Hi everybody, today we're going to have a look at some common problems that are set in differentiation topics. Typically they relate to finance, revenue, profit, and unit cost, measurement, volume and surface area, area and perimeter, and motion, speed, distance, acceleration, velocity, and displacement. Now, each problem tends to require some sort of optimization, finding a maximum or minimum, the desired average or instantaneous rate of change, an initial value, or a value at a point. The following examples demonstrate how calculus can be used to do these things. So here's example 1. That's going to be a finance problem. So a ticket company knows that the number of tickets sold impacts on whether a show is successful. Determine the optimal sale price if the following is known. If tickets are free, the show sells out, but they make no money. In fact, they'll make a loss. For every $1 increase in ticket price, 10 less people attend. Now, the maximum capacity of the venue is 2,000 people, and the cost of the show running is $20,000. The number of people that attend is N, the cost of tickets is C, and we're going to assume that no more than 2,000 people wish to attend, because that would change our formula if that was the case. We're going to ignore that case, we're just going to work with what we've got, and assume that these two statements are linked. Now, the first thing we'll have to do is state an equation for revenue. So how do we work out how much money we get for the amount of people that attend? So we start with 2,000 people for the number of people. Oh, actually, we should start with the revenue formula. Revenue equals the ticket price, C, lowercase c, times by the number of tickets sold, times, that's lowercase n. So the number of tickets sold would equal $2,000, take the cost of the ticket, so if it was $1, 10 fewer people would attend, so N would be 1,900 people. If C was cost $2, 20 people wouldn't attend, so that would mean 1,980 people would have attended, so on and so forth. Now to get the revenue, we're going to multiply the cost of the ticket times by the number of people that attend. So if the number of people that attend is 2,000, take C times 10. That will be C times 2,000 take C times 10, which will be a negative quadratic. The profit simply is going to be the total revenue minus the cost of running the show. The cost of running the show we learnt was $20,000. So we take our revenue and we subtract our $20,000, and we end up with this quadratic here. From that, we can find the derivative profit with respect to cost, and if we equate that to 0, that'll tell us where the stationary points are. For a negative quadratic, that'll be a maximum, and we find out that the optimal profit is at C equals 100 and N equals 1,000. We can find out the N equals 1,000 by substituting back into this formula here. To find out the max profit, take the cost of 100, substitute that back into our profit formula, which is here, and that'll tell us our maximum profit is $80,000. So we should then make a statement answering the question. The optimal profit is $80,000 at a ticket price of $100 with 1,000 people attending. So we've stated an equation for revenue, we've stated an equation for profit, and we've found the optimal value for P. Now the next question is, at what ticket price do they make a profit? Well, they make a profit when, because it's an upside down quadratic, it'll be at the part that's above the x-axis for the profit equation. We know when the stationary point, we can find out when the stationary points are by, find out what the stationary points are. We can find out where the profit formula crosses the x-axis by placing in P equals 0. Solving that equation, we find 10.55 and 189.44. But that doesn't answer the question, because you can't get a ticket price of 10.55. It only goes up in lots of $1. So it'll make a profit when the ticket prices are between 11 and 189, and it makes a loss at less than $10 and more than $190. Now we've answered the question, and this is kind of what it looks like. Here's $11, here's $189, no profit, profit, max profit. Okay, but there was another way that we could have answered the problem. Instead of stating it in terms of number of people, we could have stated it in terms of cost, and made n the independent variable, and c the dependent variable. So all I've done is I've rearranged this equation and ended up with 200 take n on 10. So that would be the c part, multiply it by n. That's what I've done here. Revenue is now in terms of n, the number of people. We can find dp dn, do the same operation with the stationary point, and again we'll find that n is 1,000 and the cost is 100. And then we would have repeated the same process. We would have gotten this graph showing the number of people from here to here is the profitable region, and the unprofitable region is this region on the outside. And so the profit is, the max optimal profit is still $80,000 because we're using the same set of equations. Where the approaches get different is when you have a cost per ticket rather than just a fixed cost. So if this was plus 200N or 2N, which would be $2 per ticket, you would have had to have used this approach to make the equations work. Okay, question 1 done. Question 2, this is a volume problem. So if we have a metal sheet and we want to make a box out of it, and we cut the corners out and fold them up like a net, what's the maximum capacity of the box? Now we say capacity, so we're expecting it in litres, so at some point we're going to have to convert to that because we've been given centimetres up here. So if we draw it, we'll find that these lengths here are x, because they have to fold up and meet at the same point. This length here will be 200 take 2 lots of x. This length here will be 400 take 2 lots of x. We fold them up, it'll be that length times x, which is what I've done here. If we take the derivative of that, we get this equation here. Now v is going to be a positive cubic, so the local maximum is going to be the first value that we get to. Positive times negative is positive. So if the stationary point's at dv dx, that will give us that equation. Solve it, you'll have 42.265 and 157.74. This will be the maximum. So if we have positive cubic, the local maximum is always the first value. So we can find the maximum value at 40, well, we can find the volume at 40, no, it's not the maximum volume, we don't know that yet. The volume's at 42 point, the local maximum volume will be at 42.265, which is this volume here. And we can find the capacity at that point will be that many litres. Now the problem that we face is that the maximum capacity could also be at either one of the extrema, down at when the length is 0 or when the length is whatever its maximum is. The logical maximum would be 100, because 200 take 2 times 100 would be 0, so that would be the base would be 0. The base can't be less than 0. It's no point looking at this because as soon as that hits 0, it no longer becomes a box. So if the max is 100 and the minimum 0, they're the extrema. Quite logically, it's not going to be, the maximum volume is not going to be one of the extrema because the volume of the box at that point is 0 as it collapses on itself. But we should check it anyway, just for the sake of completeness. At V0, substituting 0 into this equation, we find out the volume logically is 0, and the same as at 100. The graph should look something like this. 0 and these 2 points here, 100 and 200, the solves of those two brackets. So looking at that, we can now make our statement of the maximum capacity. Therefore, max capacity at x equals 42.265. So answer the question though. What is the maximum capacity? So we need to state what it is of 1535.6 litres. There we go. Problem solved. Next question. This is a motion question. A particle is traveling in a straight line such that its displacement from point 0 is described by s equals blah for 0 to 200 seconds. And let's say this is in, I've already said this is in meters. So how far is the particle from point 0 at t equals 0? Well, substitute t0 into this equation, you get 200 meters. When does the particle reach point 0? So that'll be when the displacement 0. It does it at x equals minus 5, which is out of the range. So it never reaches the origin. The next question is, when is the particle stationary? The particle stationary when the velocity is 0, quite logically. So the particle's stationary at 2 points if we find the derivative and equate it to 0. And that's at 0 and 2. What is the initial velocity of the particle? Substitute in for t equals 0 into the velocity formula. It's 0. We knew that from here. And E, as t tends to infinity, what happens to the velocity? Well, if we take the velocity formula and substitute in infinity, we just need to look at the highest order term. Infinity squared will still be positive. It will tend off to positive infinity. F, what is its maximum displacement? So its maximum displacement is either going to be at the local max or at the extrema. So we're going to test all three. The local max is also the lower bound at 0. So that's going to be 200 meters. At S2, the minimum, the local minimum, it's at 196. So it's not going to be that one either. And at, we didn't have to test for this, but we did it anyway. S200 is the maximum defined by the question, which is, what's that? 7,880,200 meters, which is definitely the biggest value. So its maximum displacement at t equals 200, and that's a huge value. And this is kind of what the graph looks like. When it gets to 200, this graph's going to be up here somewhere. And there we go. 3 examples of using differentiation to solve problems. Thank you, everybody.